Hello and welcome to this webinar titled Engineering First Principles, Applications to Pharmaceutical Manufacturing, hosted by Biopharma Asia magazine and presented by Dr. Bernard Mugabe, PhD of Chemical Engineering. My name is Stephen Edwards and I will be your moderator. Before we begin, I would just like to inform our viewers that there will be a live question and answer session after the presentation near the end of the webinar. Audience members can send their questions in at any time during the webinar via the Questions tab located directly below your webinar screen, and we will go through these at the end of the webinar. Now please allow me to introduce today's presenter. Dr. Bernard Mugabe retired as an engineering fellow at Eli Lilly and Company at the end of 2017. He has a BE and a PhD in chemical engineering from the University College of Dublin, Ireland. He spent 34 years working for Eli Lilly and Company at various locations in Ireland and the USA. He has held a variety of roles in process control and process engineering over this time, as well as time in corporate manufacturing. His main interest is in the application of first principles, thinking to improve engineering and management decision-making and problem solving at Eli Lilly, covering both process development and manufacturing. Over his career, he has completed projects in all the various types of pharmaceutical operations: API, fill finish, medical devices, and animal health. Towards the end of his career, he has applied first principles-based approaches to pharmaceutical cold chain distribution, leading to improvements in both the speed and quality of decision-making in this area at Lilly. I will now be handing over to our presenter. Welcome, Dr. Mugabe.
Oh, thank you, Stephen, for that introduction, and good morning or afternoon to everybody who is attending the webinar. As Stephen said, my name is Bernard Mugabe. I worked with the Lillian Company for my career, pharmaceutical industry, of course, and basically I was for a lot of my career, I was part of a corporate engineering group, basically, who did projects all over the globe for Lilly plant sites and facilities all over the globe. And as I said, my main interest was, always has been, is applying the fundamental first principles of engineering to solve problems, mainly in manufacturing, because that's where we were located, but also for process development, on the basis, of course, that it's worth your while to make sure that process development is done well, because then it makes life an awful lot easier, of course, in the manufacturing world. And of course, recently with the focus on quality by design and stuff like that, that becomes even more important as we think about things like that. I want to start off by just giving a background example of why this kind of thinking can be is very, very important. And there's many examples out there I could pick, but for this particular webinar, I just picked one example. If anybody's familiar with it, it's an example from an explosion that happened on the MV Alpha Cape back in the 60s. And the basic idea of what happened was the Alpha Cape had been involved in a collision with another ship out at sea, and there had been an explosion, and basically the Alpha Cape itself was part of that had been damaged. And so it was towed into harbour to be repaired. And obviously, you know, a ship is designed to be transporting materials. So basically, there's a big push to get the repairs done as quickly as possible. The Alpha Cape was transporting a flammable naphtha material. So when it got into port, the regulations, of course, stipulated that before anything could be done, it had to be inerted using, SOP said it had to be inerted using gaseous nitrogen. Now, unfortunately, at that particular point in time, there was no nitrogen available. But somebody found a set of canisters of CO2, carbon dioxide. And so somebody proposed the option of using carbon dioxide to inert the the hold of the ship, rather than the SOP nitrogen, which just was not available and would not be available for a period of time, again meaning that the ship would be just sitting there and basically not earning money for the company and not doing what it's supposed to be doing. So obviously this was a change of procedure, and it's one of those classic cases where you have the typical conflicts we all have to deal with, where you have an SOP that says to do one thing, but circumstances are such that you can't in the short term, and you're under pressure to move ahead from a business and financial perspective. And obviously that ship had commitments to customers, and if it's being repaired, it's obviously there's going to be an impact to those customers. So there's a lot of pressure to get the repairs done as quickly as possible, and in particular get the unearthing done then as quickly as possible. So a decision was made to go ahead and unearth with CO2, since CO2 is like nitrogen in the sense that it's not flammable. And during the unearthing process with the CO2, there was a major explosion, and 4 people were killed as part of the explosion. In the aftermath of making the investigation as to what actually happened, the issue turned out to be fairly straightforward. Is that, of course, when you take your CO2 cylinders and you open them up, as the CO2 escapes, you get a Joule-Thomson effect and a cooling effect. For nitrogen, it's not an issue, but for carbon dioxide, one of the offshoots of that cooling effect is going to be the formation of solid particles. And of course, we all know that solid particles have the ability to pick up small amounts of static electricity, which in this case apparently is what happened. And that became the source then for the flammable material to actually ignite before it could be fully blanketed by an inert atmosphere. So you look at this and you say to yourself, people were really fully aware of the first principles involved in handling these kind of materials like CO2, then they might have stopped and actually considered what the ramifications would be of the action they were about to take. And they might have spent a bit more time doing risk analysis and this idea, of course, of CO2 forming small particles due to this cooling process as the gas escapes the cylinder was not unknown, and you even see it in household cylinders. But again, not taking time to actually consider what might happen from a basic first principles, in this case from a thermodynamic perspective, led to people doing something that they, in retrospect, really shouldn't have done. And this type of example appears many times. You can find examples yourself where this kind of thinking has led to a major incident, and in retrospect, some simple first principles thinking about the basic physics of what's likely to happen could have actually prevented, but it was never done because the pressures to keep moving ahead were so great. Now, when it comes to problem solving and problem analysis or analyzing situations, there's 2 key attributes of problem solving that we want to be aware of. The first thing is we want our problem solving to be effective. What does that mean? Well, it means that you want to get the effects you desire without any unintended consequences. So in the case of the previous example, the effect we wanted was to blanket the ship and its hold, get that blanketed, without any negative unintended consequences. In this case, of course, the unintended consequence was the fact that there was an explosion. And so when you want to do something, when you want to be an effective problem solver, is how can I get the effect I want without an unintended consequence? And so, for example, if you think about that from the pharmaceutical world, it's like, how do I make, for example, a process change such that maybe it's, for example, it's to increase the yield, it's to improve the quality of the product, it's to reduce the cycle time. Whatever it is you might be after, that's the effect you want. But then how do you do that without any unintended consequence? So in your attempts to increase the yield, you make things more unsafe. In your attempts to improve the quality, you reduce the cycle time, and so on and so on and so forth. So that's how you judge the effectiveness of a problem-solving process. The second aspect, of course, is that we want to be efficient. Now, efficiency, of course, is simply about being effective, but using the minimum resources required. Now, this whole issue of interplay between effective problem solving and efficient problem solving has been studied. And one of the thought processes about it is this idea of system 2 versus system 1 thinking. And this has been pioneered by a psychologist named Daniel Kahneman, who actually won the Nobel Prize in economics for applying these ideas to economic theory and in particular decision making. And in fact, he has a book out, if you ever get to read it, called Thinking Fast and Slow, and as I said, by Daniel Kahneman, Kahneman, where he talks about this. And what he comes down to is he says you have to realize that the human brain has two ways of thinking, two systems for thinking, system 1 and system 2. And system 1 represents that fast-acting, intuitive thought process that we have, whereas system 2 is the more logical and analytical side of the thinking process, if you like. But of course, it's slow. And what happens is when you're faced with a situation, faced with a problem, faced with anything, unfortunately, the way our brains are wired is we immediately jump into system 1 thinking. We can't avoid it. It's just the way our brains are wired. We have to consciously actually invoke system 2 thinking. And so if you stick with system 1 thinking, that intuitive approach only, what tends to happen is you expose yourself to what are called cognitive biases. And these cognitive biases tend to lead us astray. They give us a false sense of security in the solutions we're coming up with. And once we get those solutions in our head, they get locked in and they become very difficult to essentially extract out of our thinking process. And so the only way to circumvent that is to actually thoughtfully and introduce our system 2 thinking, which is to say is that kind of analytic approach. And what that's going to do for us is it's going to essentially, first of all, slow us down a little bit, cause us to catch a breath, and actually begin to ask more detailed questions about what might happen, what's the physics of what's going on, what does that tell me? And in doing so, it actually makes us ask better questions, get more detailed, and as well as increasing the probability that we get the effect we want, it actually increases the probability of identifying unintended consequences with the actions we might be proposing. So what we want to do, like I said, is have methods for moving from system 1 thinking to system 2 thinking. And the basic idea is that when you start practicing that use of the fundamentals, the fundamental first principles, you're going to find that naturally causes you to invoke your systems 2 brain activity, if you like, or thinking processes much more frequently, and therefore you're going to do a better job in the problem solving. It's also efficient because you don't have to invent the first principles. And that's a big part of this, is that all the first principles you might think about, and we'll talk about some later, you're not inventing those. The work has been done for you, and what you're really doing is you're basically building on the work of people that have come before you, and all you're really trying to do is to apply that to your specific situation but you don't have to reinvent the wheel. Essentially, these first principles will be things that you can bank on, if you like, and therefore you can have great, if you use them correctly, you can have great confidence, in fact, that these will be useful and get you to where you want to get to. So as I say, efficiency is about being able to reuse learning and techniques that have already been developed, so that you don't have to redevelop them from scratch, and you can take advantage of all that learning that has come before you. So what are first principles? Now, when we think about first principles and we think of examples, very quickly we get into mathematics. Most first principles are expressed by some sort of mathematics, like, for example, the ideal gas law. Hopefully we're all familiar with that. PV equals nRT. That's a first principle. From an engineering perspective, that's a first principle. And a lot of these then are expressed in terms of mathematical relationships. If you're in electrical engineering, you know that the voltage is the resistance times the current in a DC circuit, kind of a framework. So they basically all are mathematical in terms of the way they're expressed. However, I think it's very useful to have a definition of first principles which is not mathematical. It's more about the idea than anything else. And so how I define first principles, the first principles are govern the behavior of a system, that govern the behavior of a system are the fundamental causal physical relationships that constrain the behavior of a process or system. That's the basic definition of a first principle. So we're focusing here on those things that constrain the behavior and therefore allow you to think about what's going to happen. But the application of these first principles can tell you why a system behaves in one way rather than another, and can be used to predict the future behavior of a system with a higher level of confidence. And that's the basic idea. So if we go back to the simple example of PV equals nRT, what that simply tells us is that if we have a fixed mass, fixed volume system and we increase the temperature, then the pressure is going to increase. If we didn't have the constraint associated with this first principle, we wouldn't be able to make that statement. Another trivial example would be if you hold something in the air and let it drop, let it go, it's going to fall to the ground because of gravity. If we didn't have gravity, as we have in some places, like in space, if you let something go in space like the astronauts do, the impact of gravity is different, and if it's far enough away, it's essentially negligible. If you're away from any gravity source, it's negligible. So when you take your hand away, essentially what you're holding really wouldn't move at all because there's no gravity there. But once we know we're in a gravitational field like the surface of the Earth, we know exactly what's going to happen. Gravity is going to take over, and whatever we were holding will drop to the ground. So again, a simple example would be, a simple process where you have reactants going in this case reactant A, B, and C, all going in, 30 kilos of A, 50 kilos of B, and 20 kilos of C into your process, and you're producing some output streams, Y. And we know that a steady-state mass balance on this process, let's say it's a continuous process, then the steady-state mass balance we expect to see is that the sum of the outputs is the sum of the inputs, which in this case should be 100 kilos. So that's a fairly, the idea of mass balance is a pretty fundamental first principle. But of course, it's not the only first principle that's active in a system. So for example, if you went out and actually made the measurement of all the output streams, you might end up with 101 kilos, for example, in your output measurements. And you say to yourself, well, that's not equal to 100 kilos. I know mass balance is a pretty fundamental first principle. So if you saw that the input was 100, the output was 101, your initial instinct is not going to be to call the Nobel Prize Committee and say, I've created 1 kilo from nothing, give me the next year's Nobel Prize. You're going to say, well, I know mass balance works. Therefore, if there's a difference between the input and output, there must be something else going on that I've forgotten about. that I haven't taken into account. And of course, in this case, it's not difficult to imagine things that could have happened that would cause the 101 kilos to be different on the output side than the 100 kilos that went in. For example, all of the outputs and all of the inputs have to be made by some measuring devices. And we all know that measuring devices have measurement error. You can't measure something exactly perfectly all the time. Therefore, you always have measurement error. So one possible explanation is for this difference is that it's measurement error. Now, measurement error, of course, has its own set of first principles, and I can apply those to my situation and work out what the measurement error contribution should be. So let's say, for example, I've done that exercise, and what that tells me is that based on the inputs I put in and the measurement errors involved, I would expect to see on the output side 100 kilos plus or minus half a kilo. That's what my measurement analysis tells me. That the worst case error I should see is about half a kilo. Now I've taken the measurement error into account, but I still have a discrepancy. I've got 100, maximum of 100.5 I would expect taking that first principle into account. But I still got 101 kilos to explain, so I've still got a half a kilo to explain. And so now you start looking for other places. Maybe, for example, some of the data was transformed into a spreadsheet to do the final input-output calculations, and maybe somebody transcribed the number incorrectly. But you could start asking those kinds of questions. However, if the error analysis said that the output could be anywhere between 100 plus or minus 2 kilos, for example, based on the measurement error of the instruments, etc., involved, then if you've actually got 101, you would say, well, that's consistent with both my first principles of mass conservation and my first principle of the measurement errors involved. Therefore, I basically understand how this system is working, and I shouldn't be surprised by the 101 kilos of output that I got. So that's how first principles work. They provide you a set of principles the system should obey. If the system obeys those, it's going to be obeying those principles, then you're in good shape and you can begin to think about making predictions. If not, then there's a discrepancy, and that's an opportunity for learning. Don't ignore it, understand why, because that discrepancy could come back to haunt you. Because if you make a prediction based on a system you don't fully understand, then obviously you open yourself up to the risk of making significant errors, and that leads to trouble down the road. And of course, in a batch process where you can have accumulation in your process, then the sum of the inputs minus the sum of the outputs is just the accumulation in a given time frame. So that's just the unsteady state version. But that's the basic idea behind the application of first principles. And of course, conservation of mass and conservation of energy is about the most fundamental first principle you can think of. But there are lots of examples, and I've just given a few here, like conservation of energy, ideal gas law, 6 laws of diffusions, Newton's laws of motion, and Bernoulli's equation for one-dimensional fluid flow are just some examples. There's heat transfer laws, there's mass transfer laws. There's just a whole slew of these things. For example, as a chemical engineer that I either learned in college or learned over time throughout my career. And every different type of engineering discipline has their own set of first principles, and of course many overlap. So, for example, the first principles of fluid dynamics would be a place where, say, for example, mechanical engineering and chemical engineering would certainly overlap. Heat transfer would be another one where they would certainly overlap. But mass transfer is something that's typically more chemical engineering, whereas things like stress strain analysis, mechanics of materials would be more mechanical engineering types of first principles. That isn't to say a mechanical engineer can't get into mass transfer advice, or a chemical engineer can't get into modeling stress strain situations, because I've done it myself as a chemical engineer. But it's not your core kind of set of first principles that you associate with your particular branch of engineering. But as you grow in your career, you're going to start branching out into other areas that you weren't familiar with. And of course, that's hopefully the advantage of a good engineering education, is it not teaches you specifics, but it also teaches you how to learn and how to grow their learning and their understanding over time. Now, some points to note about first principles is, first of all, they are dependable. Like I said, conservation of mass, conservation of energy, they are, in the world we live in, they are dependable. Now, of course, if you're talking to a theoretical physicist, things like conservation of energy, you have to put some caveats on, because we know about things where in the short term, for example, with Heisenberg's uncertainty principle, you can have a discrepancy with your energy balance, but only of a very small time element. And that's quantum mechanics, not something we need to worry about as chemical engineers. The next point is that first principles analysis can provide deep insight into why something happens, as well as the fact that it will happen. And this is very useful when it comes to explaining to people why you're proposing the changes, for example, you're proposing. So it makes justifying changes easier, because you can say, you know, this is the right answer and here's why. And you can give people a very clear picture, or a clearer picture of why, because you understand the first principles, you understand what's affecting what, and hopefully you found good ways to then explain to people, maybe by making nice little analogies and stuff like that. For example, in a project I did probably about a year and a half ago now, about 2.5 years ago now, I used the analogy to explain to people why I was proposing the change. I used the analogy of a rocket plane taken off at an angle to at an angle, so that by the time it got to the end of its runway, runway, it would actually be pointing upwards and have enough momentum to keep going and to keep flying, like old flying rockets of days gone by. That turned out to be quite a useful analogy for the change I wanted to make, and you kind of think, well, that's a very unusual analogy to make in a pharmaceutical industry, but sometimes those things actually work. And again, it was because I was trying to make a point about the first principle that was actually going on. The third point is that first principles do have regions of applicability. So, for example, if you take the ideal gas law as a simple example, PV equals nRT, there are regions over which that's applicable. And so basically the whole idea is that the higher temperature, the more applicable the ideal gas law, the lower the pressure up to a point, the more applicable the ideal gas law. So, for example, in the pharma industry, we tend to think about pressures, tend to work with pressures that are close to atmospheric. So that's kind of the reason we think about it. And in that reason, first principles tend to be, or the first principles of the ideal gas law tend to be very applicable for normal temperatures and pressures. But for example, if you were to have a process that involved CO2 at 300 psi, for example, and in some industries, like in the pharma industry, 300 psi is a large pressure. Some industries it wouldn't be such a big deal. But if you were working with carbon dioxide at a pressure of 300 psi, then using the ideal gas law would be off by 12%. So you have to add that compressibility factor in there, Z, and you have PV equals ZnRT, and Z would actually be 0.88 for carbon dioxide at 300 psi and psig, that area. So, you know, you have to know your regions of applicability to make sure that you're applying the first principles in a region that they actually make sense. Another place where you have to be careful with the ideal gas law is if you're talking about freeze drying. In freeze drying, the freeze drying is done at really small pressures. You could be talking about pressures in the region of 100 millitorr. And in those cases, you have to be careful because the intermolecular distance between the molecules of air is much greater than the molecular size. And therefore, some of the normal assumptions you make about air being like a continuum don't apply anymore. So again, you have to be careful. The next point is that real systems or processes are impacted significantly by many first principles at the same time. And this is what makes life more complicated, but also more of an opportunity to see the benefits of using such principles, is that it's rare that you have a system which is governed totally by a single first principle. Many times you've got the ideal gas law, you've got the heat transfer laws, you've got some mass transfer, you've got lots of things, maybe some fluid dynamics, all of these things are going on. And the challenge is, and the reason why it gets difficult in the first place is that, trying to deal with all of those at the same time becomes very tricky. And so the idea is, by using a first principles-based approach, it makes it easier to take all those things into account at the same time. And that's particularly true these days, as we've seen significant development in the available software and hardware that are available to people now to help you solve these problems. And one of the things I like to point out to people is that when I started off working back in 83, 84, the process control computer I worked with at the time had 64 kilobytes of memory. And my modeling computer that I was using before I left Lilly had 196 gigabytes of memory. So we've gone from 64K to 196 gigabytes in 20, 30 years. That's a lot of progress. You couldn't even, it would be hard to see 64K of memory anymore now. It would actually be so small. The other point to remember about first principles relationships and why, again, it makes different behavior that bit more complicated is that they're nonlinear in general. And so, a lot of times we work with statisticians who always start off with linear type models, or as most models with both linear and quadratic terms. Those models tend to be successful only because you've already fixed the process and you're looking for small changes relative to target. So you're looking at asking the question, how does the process behave away from target but close to target? But in engineering, we're faced with other problems where we're actually trying to infer the behavior of the real system from models that may be much smaller in scale, for example. So you might be doing studies. The studies might have been done in a 2-liter vessel in a lab somewhere, and that has to go to either a pilot plant or a plant where the scale could be going maybe a factor of 100. And to assume that relationships would be linear over that kind of a range of scale would be very dangerous, and in fact, just not true. And you would be, if you try to design based on linear assumptions over those kind of scale changes, you'd get yourself into big trouble very fast. And that's of course, the whole challenge with scale up. And by scale up is such a challenging process. Then finally, something to note about first principles is they are reproducible. What I mean by that is, let's say, for example, you go into a lab and you do a set of experiments. Say you did 20 experiments over a week or something like that. And then all the results, all the output of the process of the experiments, the samples are sent over to a lab for analysis. And so maybe that takes a few days to get that back. And so when you get the results back, everything looks fine except there's one anomalous result. Well, part of the issue you get into with the physical experiment is that in trying to understand why did you get that anomalous result, it can be very tricky, because now you're faced with how do I reproduce the conditions that gave me that anomalous result? Maybe I just can't even do that because I wasn't measuring or taking note of the thing that caused the anomalous result, and therefore I can never reproduce it. So there'll always be this thing in the back of your head. Is that anomalous result due to something real or something that was unusual in the lab setup at that particular time? Very difficult question to answer. However, with first principles applications, if I get an anomalous result, when I run do a simulation, for example, I can reproduce that there on the spot and see do the analysis on the spot. I can reproduce my environment pretty accurately for that particular simulation. So that's an advantage of first principles that you mightn't get in physical experiments. So as well as saying what first principles are, it's important to remember what they're not. They're not empirical statistical modeling like linear regression or nonlinear regression, design of experiments, DOEs, heuristics or rules of thumb, guesses based on past past experiences, whether those experiences have been successful or unsuccessful, or vendors' recommendations. However, of course, all of these things shown here on this slide are important in everyday engineering work. But the whole idea is we're not saying that use of first principles is a panacea and you can throw everything else you've learned out the door. It is just another thing that you have in your toolkit, and recognizing where to apply it, and apply it most effectively and efficiently. That's where you're going to reap the best bang for your buck, and that's where experience comes in. And that's why you have to start doing it, and then you learn how to do it better. It's like everything else we do in any endeavor that we undertake. But it's important to remember that there will be times when the best answer is to do a design of experiments. That is the most practical approach to take. There will be some times when heuristics are good enough for what you're actually being asked to do. So, as I said, we don't throw these things out. They are there to supplement what we're actually doing. Now, I also wanted to mention about a first principles approach for implementing first principles, and this is just a very high level approach that we take. But the first step, like in anything else we do, is planning. And that's where we talk about what the opportunity is, what the pros and cons of doing a first principles-based approach might be over other approaches that we just talked about. And the basic idea is that at the end of the planning phase, the important question you want to be able to answer is a first principles-based approach appropriate? And the answer might be yes, or the answer might be no. And it's important to do this because, again, it's the old story about, it can take a long time to get a customer, get them on your site, but it's very quick. You can be very quick to lose them. So I've always found that being honest about this is very appropriate, because what I'm going to do here is I'm going to make a decision with the customer about whether or not we should proceed ahead with the first principles-based approach. I'll present the information to them. I let them know what the risks are, and if it's a situation whereby the risk is that we might do this and not learn anything from it, that's a real risk. I want them to know that, so that if that's actually what ends up happening, then we shook hands at the beginning and said, we're both going into this with our eyes open, but this might not get us anywhere. The customer might still want to do that, because there might be an awful lot of money on the table. And this might be a huge opportunity, and they really want to do it. So it's very important to spend the time up front working with the customer to really understand what they're after, what questions they need to have answered, what decisions you're trying to make, and then basically use your understanding of the approach and the first principles involved to work with them to say, I think this is a good idea and we will get some benefit, and here's what I think will happen. Or this is just a poor idea. Let's not proceed ahead, and let's take an alternative. Go back and take an alternative approach. This isn't going to work. But if we decide the answer is yes, then of course the next step is we create the first principles application, which might be a model, it might be a calculation, who knows. And then once we've created it, we have to confirm it. We have to do some level of confirmation that what we've produced actually means something. And once we've confirmed that it actually means something and is useful, then we implement it. And I always like to quote the Deming quote as well. Either W. Edwards Deming or George Box. Their quote was, all models are wrong, but some are useful. So at the end of the day, what we're trying to do here is we're trying to create something useful. So when we do this confirm phase, the question we're asking is what we've created useful? Is it going to help us to answer the questions we need to answer, and so on, and make the decisions we need to make? And then once we've done that, we implement the recommendations of that, and then we monitor those, see if they're successful, so that not only can we then record the success, hopefully, that we've had, but if things didn't turn out quite the way you think they should have, and that often happens, maybe you only get 80% of the benefits you thought, not the other 20%, that's an opportunity to learn. And so then, you learn from that, as somebody who's applying the first principle, so that next time, hopefully, you'll be more accurate in your predictions. Now, one quick thing I wanted to talk a bit about is how do you go about testing applications? So if you talk to somebody outside of the pharma industry who is used to working in this space, maybe somebody, for example, in the auto industry, and they're using models and first principles thinking everywhere to design their automobiles, or maybe somebody in the aerospace industry, and you ask them about confirming the model, they'll talk about verification and validation. So the idea is that when they talk about verification, they talk about making sure that the model is doing what you've asked it to do. That doesn't mean it's what you essentially have asked it to do is correct. It's just that it's behaving the way you think it should behave. That may be still incorrect because you've modeled it incorrectly, but this step just makes sure. So, for example, an example would be in let's say I have a model where I have stuff going in, that mass balance model. So I've made a mass balance model, I've got stuff going in from one side of the model and stuff coming out. Well, my model should predict the same amount on both sides. That would be an example of verification. Now, there still may be problems with the model, but at least I know that part of it. That gives me some confidence that I set up the model correctly. Then validation is about making sure that the model actually gives results that confirm to reality. Because that's what you need before you can start using the model. You need to have some validation that the model is giving you accurate enough results. Now, the problem with pharma is, of course, validation has a lot of connotations about it. So what I've seen happening is what some people are doing now is this actually came from work I did on the cold chain. The vendors of cold chain solutions that do modeling of their containers, they don't talk about validation of their models. What they do is they talk about calibration of their models. So basically, the calibration step would be where you actually run the model against in their case, it's a container that's changing product temperature in response to ambient conditions. So you do a test, and you'd see what the actual product temperature variation looks like. And then you run the model. And if they're close enough, then you would say that model is calibrated. So calibration in this case is what other industries would call validation. It's just making sure that the model gives results that make sense and agree with reality. And then that allows us in the pharma industry to leave the term validation for something that more adheres to regulatory requirements for some of the more important models. And this to me would be reserved for models where you're putting, for example, the model online. So maybe you've developed a first principles based model that decides whether a piece of product, maybe it's a capsule, maybe it's a vial or a cartridge, you've got a model in there that looks at some parameters and has an algorithm that makes a decision as to whether this cartridge or capsule or tablet needs to be accepted or rejected. So in that case, that would be, let's say, would be implemented in the computer control system, and that should follow the normal validation processes like CSQ, computer system validation process, and those regulate, the requirements for such validation is already out there, and you would just follow those things. But I would argue that that's a very small few, and online modeling, it's not something you get into day one. That comes after a bit of experience. So basically, verification and calibration really cover most of the models, and certainly most of the models I've been involved with over my career. Because putting these models online is only a more recent thing, and usually happens in development, whereas I've typically been located in manufacturing, so I haven't really had much of an opportunity to put models online. Now, what opportunities are out there for using first principles? And so one of the exercises I did at Lilly when I was working there is I used to keep track of first principles applications, the ones that I did, that my team did, and then as I talked to other people, there were other people out there, of course, doing this in the various manufacturing sites, and so they would send me their examples. So I kind of built up a little database of examples. And so one thing I was really interested in was, what are the kind of situations where people would be using a first principles based approach as distinct from something else. And so what I found was that these are some of the main opportunities I saw where people were using first principles. The first one was, we talked a little bit before, is managing the risk when implementing a change to the process. Another one, my favorite one, was identifying the causal factors, root causes for manufacturing issues, or importantly, showing that a hypothesized causal factor, for example, is not relevant in a given situation. That can be very useful if somebody proposes, because what tends to happen in a root cause analysis is, the very first step is you try and think of everything. What are the things that might be a causal factor in the particular situation where we're analysing a particular incident that occurred? So if you can come along and say, well, I can very quickly tell you that can't be the issue, then that's very useful for people, because now they can discount that quickly and not carry it forward into the more detailed aspects of the analysis. So that's a thing to remember. If you can discount potential causal factors, that's very useful. Obviously, process optimization efforts, such as might be carried out as part of a continuous improvement program, that's opportunities. Sometimes you just don't have a physical testing system available to you. It can be used for creating more reliable designs for process equipment so they work properly the first time. And then alternative approaches are too costly or require too much time. In this case, for example, let's say, for example, we've had an incident in manufacturing, and you go back to the production people and say, look, we need to do some analysis on the production system to find out what went wrong. But if they've already been through an incident, that means they're probably behind in their schedule. The last thing they want to hear is they need to give up more of their production time, because they're already behind. So being able to solve the problem offline, and again, this is something I found very useful. Production would really be very grateful to you if you found a way to get to the root cause without them having to use any of their resources, if you like. That was very beneficial to them, because they're trying to get back up and running, et cetera, when they have had a manufacturing problem. And then finally, if the first principles of the system are well understood, easy to implement, then that's an obvious example. And a good example of that, done loads of times, is basically doing calculations around water, for example, water distribution systems or glycol distribution systems. They're very easy to model. If you have the right software, they can be very quick to model. Usually the bottleneck to modeling it is not building the model, it's getting the data. So you've got to go out there and look at the line, find out the line sizes and the valve types. And now if you have a good system where all that data is recorded, it can be easy. But sometimes you just have to go out and go out to the field and get some of that information. But once you've got that, then understanding the fluid flow characteristics, pressure drop versus flow for your entire system, if you use the right software, it can be very, 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 very easy. Finally, I would like to make you aware of the fact that I have been working with the International Society for Pharmaceutical Engineering, and what I've done for them is I've built a 2-day training course that goes into some of the stuff we talked about here, but in a lot more detail, with lots of examples that we work through, which are based on my own experiences and the experience of others. So they're practical examples, which will help you to see how you might begin to use these principles much more effectively and efficiently within pharma manufacturing, and then ultimately, of course, process development as well. It's course T60. In fact, I just presented this course last week. It was the first major presentation of the course last week to 24 attendees, just after the ISP annual meeting in Las Vegas, and it seemed to go pretty well with the attendees. So that's just something to note of. If you're in the US and you're interested, the next presentations of this will be in May of next year, and then next November, again at the end of the annual meeting. I think that's scheduled to be in Philadelphia, if I remember correctly. And of course, if you wanted to bring such a course into your company, then you can either work directly with me or you can work through ISP training if we wanted to make that happen. So that's just something I wanted to finish off with to let you know. The other thing to finish off here is, I and some of my colleagues have published on this kind of work over the years and various different articles. And in fact, in the next couple of months, I'm not sure when they've actually scheduled, the paper has been accepted by the PDA journal for publication, but it's an experimental and modeling project we did to understand how vapor phase hydrogen peroxide would be absorbed into syringes. Vapor phase hydrogen peroxide is used to in isolators to actually kill obviously the bacteria and stuff, but you can't avoid the syringes being exposed to some small amount of the DPHP, and so it's good to know what are the principles and characteristics of how that's absorbed into you, but potentially as syringes with product. And so we have a paper coming out on that, which talks about not only the experimental results, but also some of the modeling results. And in fact, one of the aspects of the behavior came out by, I extrapolated the modeling results outside of the experiment, saw something interesting that nobody had anticipated, and then we went back and did the experiments to verify and validate that, or I shouldn't use the word validate, but to verify that yes, in fact, this unusual behavior we hadn't been expecting was actually seen in the real system. So it was a real phenomenon that the modeling had picked up before. And that's what sometimes happens, is the modeling, will pick up something that you hadn't thought about, or certainly hadn't thought about it in that particular way. That's why I want to have a model. It's nice to play with it. And you can do that because you're using up computer time, which is pretty cheap, rather than expensive lab time, where people are much less likely to allow you to, of course, to dabble. The other thing Stephen mentioned when he was going through my bio was that one of my interests has been applying these first principles to cold chain transportation of pharmaceutical products, particularly, for example, biologic products, which for the most part must be maintained within 2 to 8 degrees, which is a big challenge for pharma. And on the basis of all of this, I've worked with ISTA, the International Safe Transit Association, and they have I've written a new guidance document for them, which is either already published or is in line to be published by them fairly soon, on how to analyze ambient data to essentially come up with a testing profile, so that you can program your chamber with this testing profile, so that when you test your containers, you can prove that to any regulator that the profile you use to test the container is a good representation of what the container is likely to see in practice, and therefore the qualification of the container is a valid qualification. So I just thought I'd mention those two. So with that, I'm open to any questions you might have. I'll say this has not been a very in-depth, because, as I say, I have a full 2-day course. I just wanted to hit some bullet points just to tweak your interest, and as something that you might want to pursue, either at your company or even delve into it, as what's happening in your company in this space. But also, if you're interested in pursuing some training and stuff, obviously, as I said, to ISP, we have something now we can offer you.
Great. Well, thank you for that presentation, Dr. McGarvey. Now, as you mentioned, we will begin the question and answer segment of the webinar. But once again, I would like to remind the audience that you can still send your questions in via the questions tab located directly below your webinar screen. So now, our first question is, what was the biggest cost impact you have had with a first principles application?
Interestingly enough, probably the biggest was one I did close to the end of my career was we had a product that we were selling as much as we could, and so everybody was it was a device manufacturing line, and there was one particular area of downtime that people were focused on, and they didn't know how to eliminate it. So the engineer on the process came to me, and we modeled it up and came up with a very simple fix, implemented the fix, and the downtime disappeared. And that turned out to, in terms of sales dollars, increase in sales throughput, that turned out to have millions upon millions of dollars of increased sales, because we knew we could sell everything we could make. That was probably one of the biggest ones. I also was, for example, in a project where it was a supply chain product where they couldn't figure out how to optimize the supply chain and be sure that they hadn't introduced some new risks. And that particular project, I identified a solution which allowed them to save about $7 million per year. So, sometimes the payback in these things can be quite significant. Another situation was a manufacturing site had a problem, and they had what was essentially a $2 million tank of material sitting there, and they thought they were going to have to destroy the material. So I did some quick calculations for them to show that the material was fine, and they were able to go ahead and process it. So sometimes you can get very lucky and you hit these big ones. And it's not always the case, but you can sometimes. But the only reason I got to work on those bigger projects was because of other projects I had done for those customers, and they knew that it worked. So sometimes you just have to kind of build up to these things. It doesn't always. You don't always get these big projects day one, because people are, they're trying to get comfortable with the fact that essentially in silico calculations actually mean something in the real world. And that's one of your mental barriers you have to get across to people, is that you can do these calculations, and people do them, not only in the pharma industry but in other industries, and they do mean something. You can get meaningful results from them. We have come a long way in the last 100 years with our understanding of how the world works, and we can do a lot of things.
Thank you. Our next question is, how did a focus on first principles advance your career at Eli Lilly and Company?
Well, I was probably, I can't speak for the companies, but I was very fortunate in the sense that I was for the most important part of my career, I was in engineering-oriented organizations with engineering leadership, and they had a kind of a generic understanding of the value, but what I was able to do over my career was show them this value in real time, and so what I found, for example, is that we had a technical promotions route, and one of the criteria on over time what I was able to accomplish, for example, was one of the criteria, one of the ways that your accomplishments were measured would be in terms of your first principles-based applications. And that was basically, I'd worked on that with management over a number of years, helping them to understand the importance. And so then that worked for me. So basically all my major promotions were based on the first principles work that I had done. Now, of course, at the end of the day, it doesn't matter how you got there, it's the result that matters. And so, just saying I did a lot of first principles, but if there wasn't some results there to back it up, how you help the organization, et cetera, then it would be irrelevant what you did. If what you did didn't lead to success, then you would, it would not lead to anything. So, but it was really, basically, it was what made my career at Eli Lilly and Company. I could say that.
And our next question, thank you, is how did you influence management to support the use of first principles-based approaches?
So I suppose really, management are key because, at the end of the day, management can either make something happen or not because they control the purse strings fundamentally. They make all the key decisions. That's their job. So I saw it in two ways. The first way would be, bringing first principles to bear on the technical problems within the manufacturing and development environment. So when there are technical problems, and you come up with a solution, and then you can explain to management easily how, the solution works and why it works, even if they don't understand the details, they can quickly appreciate, I think, what's going on, particularly if you've got engineering management in your chain. Your management in your chain are engineers, and they may not have been practicing engineers for quite a while, but they're still fundamentally engineers. So it makes it easy to help them. The other part of this, though, which again turned out to be very helpful for me, was the fact that management themselves have their own set of problems, but they're making these decisions, and they want to make good decisions. And so they may not always understand the best techniques to help them make better decisions. And so I was able to use the first principles-based thinking to, when they would come to me with a problem, or I'd be in a discussion with them saying, what's going on, and they'd say, well, I've got to make this decision. I'm not sure how. And then I'd say, well, maybe we can help. And I'd talk more about it, get an understanding of what's actually going on, if you like. It's kind of like the physics of the management world, if you think of it like that. But what are their first principles? What are their constraints? And then basically able to put calculations and models together that actually help them. And that was a huge impact. And the fact that, not only was it solving the technical problems, but it was helping solve their direct problems, because these are the problems they had to solve as well, but they were responsible for. Maybe it was, for example, at one point, there was a significant capital investment that was being proposed, and they weren't sure if it was a good idea, but they couldn't articulate a case. And so what I was able to do was to go back and formulate in a risk management, a quantifiable risk management way, to show them that in fact their intuition was correct. It wasn't a good idea, but now we could say why, and then that made it much easier for the customer to buy into the decision as well. But that would be my two prongs. It's help them with the technical problems, and then help them with their problems, their more management type problems, if you can.
Thank you. Well, thank you for those answers, and thank you, audience members, for those questions. Unfortunately, that's all the questions for today. But before I finish the webinar, I'd like to ask our presenter once more, Dr. McGarvey, if you have any closing remarks for our audience.
The only thing I would say is, depending on your particular situation, you may not have people who see these approaches as immediately applicable, because, like I said, some people just have a hard time understanding how stuff you do in a computer can actually make predictions that work in the real world. And so sometimes you just have to take the time to show people you're probably doing it already. It's just people are not aware. And so maybe that's your starting point, is to go out there and find out what's already been done, and then find ways to make sure people understand that what you want to do in the future is just an extrapolation of some of the things you've already been doing. In other words, it's an evolution rather than a revolution. Think of it from that perspective. That may be a way to get yourself started. That's my final remark.
Thank you. And I would like to take this opportunity to thank our presenter. Once again, that was Dr. Bernard Mugabe, PhD of Chemical Engineering. Thank you for sharing your knowledge with us. I would like to remind our audience that you can view this and other webinars on demand by visiting biopharma-asia.com/on-demand-webinars. And if you are watching this on demand, then please feel free to send your questions over to me at stephen.edwards at biopharma-asia.com, and we'll get those answers sent back to you. Thank you, everyone. Have a great day.